Hey everybody. Happy Monday evening. Hope you're all inside and safe from the storm. That's the snowstorm, I guess. I don't actually know. I don't have any windows in my basement here. I assume it's snowing. I don't know. Any of you out there? Is it snowing where you are? Hopefully you're staying in and staying safe from the snow. Tonight we're going to be looking at the lab for this week, the observations lab. So I have some of my lab supplies here from my lab kit. Hopefully you've had a chance to pick those up. I know when I was there Friday night, I got to meet a couple of you, and it looked like most people had picked them up. Um, if if you're still not with a lab, if you're still without a lab kit, please make sure you get over there. As you probably saw, we had to cancel the pickup for tonight because of the weather, and tomorrow, but we'll be there all day Wednesday. I will personally be there Wednesday from 4 to 7, but you can go anytime between 10 and 7 on Wednesday to get the lab kits picked up. All right. So if you've got your lab kit and you literally have it with you right now, um, great. You should get it out and you can follow along. There's some waiting involved in this lab, so I'm not going to actually perform the whole lab myself, but I will kind of show you how to set it up and take you through some of the important points about keeping the lab notebook and just some of the expectations for this class. All right, so let's get started. Actually, you know what? Let's wait like 2 more minutes and see if some more people join up, and then we'll get started. And I've got to kind of get my stuff situated here anyway. So as you're collecting your supplies, so for this lab, of course, you'll need the instructions, which you can get from Blackboard. You'll need all of your little strips of paper from your lab kits. There should be 5 strips. 4 of them have different names of pens on the top. So like this one says that PM. This one says V. I don't know if that's not showing up. It says V. And then you've got one. You should have one that says unknown, UNK. So that's what the writing looks like on mine. It's not going to focus on that, but UNK at the very top. Of course, they're all just black ink, so there's not any way to tell them apart, except from that writing. Le Pen. I don't know about you, but I got an extra one in mine. I have 2 that say pilot. So I actually have 6 strips. I don't know if that was a mistake or if everybody has an extra one. But hopefully you found those. All right, so you'll need those strips for the lab. You'll also need a cup. If you want to do the lab as quickly as possible, you actually can do them all simultaneously in different cups. So, if you're like fancy and you've got 5 cups, you could get all 5 of your cups out and do it simultaneously in different cups. Now, the other thing that you'll need, besides the strips and the cups, is your ruler. So that's in the kit as well. You'll be able to use that. And you need your lab notebook. So we talked a little bit about lab notebooks earlier. I definitely recommend that you use a bound notebook. These things aren't expensive. You should be able to pick one up if you haven't gotten one yet. If you just want to find some paper or something for now, that's fine because everything's going to get uploaded anyway. But it really is helpful to have everything in one place. I love these composition books. They're like $1. They actually are really durable. They stay together. I use it for cooking. So when I'm writing my recipes, and then I have everything in one place and I always know how to get back to it. Although people laugh at me because I keep a lab notebook when I cook, but hey, it works. And so we're gonna start always with a new experiment by preparing our notebook and doing some pre-lab preparation with the notebook. So to do that, you can see more details about that in the orientation module, which you probably looked at already or perhaps looked at already. But basically, we want the lab notebook to be a permanent record of what we do in the lab. And if we were actually in lab, we would be spending a lot of time on this, and I would be wandering around during the lab and looking at your notebooks and making comments and trying to help you do a better job of keeping a notebook. Because if you're in any sort of field where you have to take good notes on what you're doing, this may not be science, but it could be, like I said, the kitchen or something. It's important that you understand the right way to take notes in a lab notebook. And the number one most important thing to remember is just that it is permanent, and it is meant to be a permanent primary record of exactly what you're doing when you're doing it. So you don't like do a bunch of stuff and then go write your notebook later. In a professional lab, the notebooks aren't even allowed to leave the lab at all. So as you're doing the experiment, anytime you get to a break or a stopping point, you write down what you've done in your lab notebook. You always use permanent ink. So I've got a pen here. Always use permanent ink in a lab notebook. No pencils, no whiteout, no erasing. Everything needs to be permanent as it's put in the notebook. And it doesn't have to be perfect. It doesn't have to be beautiful. It's not like a lab report. It's a record of what you're doing while you're doing it. Now, it doesn't have to be beautiful, but we also don't want it to be so messy that you can't even tell what's going on. So that's why we prepare the notebook first. So I've got my notebook prepared here, and let's see if I can show you kind of what I've done. Nope, it's not going to come through. All right, well, I'll just put it back by my face, and I'll show you this, and then I'll scan this up and put it in Blackboard after today, so you can kind of see what I'm writing and actually read what I wrote. All right, but basically I've got a title here, observations, paper chromatography. Very important, the date. Again, talked about in a previous video, if you were in a professional lab, your lab notebook would be a legal document that proves when you did things. So having things dated, sometimes even timed, is really important for that record. So I've got my date here. And then purpose. So why am I doing this experiment? When I go back to this notebook, I want to know, what did I do this for? What was I trying to find out? So my purpose here is use paper chromatography to determine the identity of an unknown black ink. So that's the whole idea here. That's what we're trying to do in this lab. The purpose should never be something like to learn about a particular chemical concept or something like that. It should be like more concrete. Like, what are you trying to figure out? What are you trying to prove or show evidence for as a result of this experiment? And also, that won't always be clear from the directions. So you have to read through the whole lab first, understand what's going on, and then put it in your lab notebook once you've sort of got an idea of what it's all about. All right. Then right under the purpose, I always list my chemical materials. Now in this lab, it's just water. So I just wrote no chemical hazards. In future labs, we'll be using, or if for your own at-home experiments that you propose, if you're using any chemicals, you should list them here. You should list their properties like chemical formula, what they look like, and then especially and most importantly, chemical hazards. So what happens if you get this in your eye, if you inhale it, if you get it on your skin? What kind of personal protective equipment do you need for working with this thing? Do you need safety glasses? Do you need gloves? What do you do if you get it on you? Do you wash it off? Do you need some sort of special cleaning thing? And then any particular hazards that, like, is it a carcinogen? Is it, which is a chemical that causes cancer? Is it corrosive, which means it's going to burn your skin? Is it poisonous? All those sorts of things. And you can use those GHS symbols that you saw in the safety video if you want also. Now, because we're all doing labs at home this semester, I'm guessing that for the most part, our chemical hazards are going to be pretty low compared to what we might experience in the lab. But, you'd be surprised. The stuff you have around the house that you think of as pretty tame can actually have some hazards if it's not handled properly. So it's worth looking those things up in the safety data sheets. And if you want more information about that, or like an example, look in that orientation module. There's some information about keeping a lab notebook that you will see. You'll see some more information, some more examples there. But for this lab, we don't really have any hazards to worry about, so it's fine. All right. So then I always like to put my procedure down in a notebook before starting the lab. Now the procedure is detailed in the actual instructions. So I don't need to copy down every single word from the instructions into my lab notebook. What I want is a general idea of what I'm going to do step by step so that I could repeat it again later. And you'll notice that I kind of wrote it in an unusual way. I wrote everything on the left side of my paper here, which might look like the right side to you because I think it's flipped in the streaming thing. But this side of my paper, and then the other side is blank, and I kind of just drew a line there. I also left some space in between my steps. So just to read you my steps, because I don't know if this is coming through, I said put about 1/2 centimeter of water in the bottom of a cup. 2, place paper strip into cup, use pencil over top for support. And 3, repeat with other strips. So it's a pretty simple procedure, right? Now all the little details about how you're going to set all that up is in the instructions, and it's okay to assume that you have the instructions with you. You don't have to copy everything from the instructions into your notebook. What you should probably do is cite that if you're in if we're not just using the lab notebook. So like when you do your individually proposed at-home experiments, you can say this lab is from, and put a citation there so that we know where it comes from if we want to actually reference the original directions. But the reason I lay it out like this is because this way I have all my instructions set up, I have my notebook well organized, but I also have a lot of space because I want to record my observations. I want to record everything I see and experience in the lab in the course of doing the experiment, because all of that might influence how well the experiment goes and what I do the next time. So I want to make sure to say things like about colors, how long are things taking, more like data type observations, how much did something weigh, error type observations, like something spilled, something I accidentally put something in the wrong container, any of those sorts of details, those should all get written in your lab notebook as they happen. For this class and in lab in general, you're not graded on your performance of the lab. Like if stuff goes wrong, you don't lose points in the lab necessarily. I want to see how you write about it and how you record this. And that's why your grade is primarily based on your lab notebook and what you write in there. All right, so for this first lab, it's just going to be one report. You're just going to put everything in the notebook and scan in your pages. For future labs, we might break it out more specifically into a pre-lab, lab, and post-lab. That's how we would do it in class if we were in person. But, since you're at home, it's kind of all happening at your own pace anyway. I feel like I don't know that that's really necessary. But it is necessary to prepare your lab before you do it, and then to think about the lab after it's done. All right, so are there any questions about lab notebook? For those of you who have yours with you, go ahead and start writing it out if you're actually going to start performing the experiment right now. Otherwise, if you're just listening, I'll just pause a minute because I don't know sometimes how long the lag is with the chat. And if you have any questions, you can put them in the chat or in Discord, and then we'll move on. All right. Okay, so I've got my cup. Any kind of cup pretty much works. If you have a very short cup and your paper sticks way out of the top of the cup, you can actually cut it. It doesn't really matter how big the strips are. And so the reason for that is, let's take a look. There's this other document linked. This is part of a free online textbook that's linked in the activities for this week, just kind of about paper chromatography and what chromatography is in general. Now, you might think of chromatography as having to do with color, and that's true in our case, and that's where the word comes from. But more generally, chromatography just means you have something you're trying to separate, and you have two phases that you're exposing it to: a stationary phase and a mobile phase. The stationary phase is staying still, and the mobile phase is moving. So in our example, the ink from the pen is the mixture, the stationary phase is the paper, and the mobile phase is the water. And so the reason this works is that some chemicals are going to stick to the paper stronger, and some chemicals are going to stick to the water stronger or the paper weaker, however you want to think about that. And so some materials are going to be pushed by the mobile phase farther up the paper, and others are going to stick more to the paper and kind of stay down toward the bottom. And so they're going to have stronger interactions with the stationary phase. Now, there are all kinds of high-tech chromatography that if we were in person, we would be doing on our fancy machines, and it makes me sad that we can't do that. There's gas chromatography. There's high-performance liquid chromatography. If you've heard things like GC or GCMS, those are professional tools that are used in all kinds of like forensics crime shows and stuff like that, where the mobile phase is sometimes gas or pumped liquid at high pressures, and the stationary phase is some sort of a chemical tube that the molecules can stick in, and you can actually separate really complicated mixtures that way and like determine if there's a trace amount of some explosives or something, some chemical. You could take a little swab off somebody's backpack, put it in one of these machines, and it separates out all the chemicals, and you could see some traces of like explosives residue, and that somebody's up to no good or whatever. So that's what chromatography is. So what we're going to be doing is similar to that. We're just using this special paper. It's not just regular paper. It actually is special chromatography paper, which is why we put it in your kit instead of just saying cut up some paper and put some pen on it. So the chromatography paper does allow this separation the way that we want. And so if we look at this figure from this book here, I'm going to see if I can zoom in a little bit here. So here's kind of what you're doing. Now, this is a bigger piece of paper with multiple samples on the same paper. The solvent, in this case water, the mobile phase, is going to be under here. And one key that you see also in our directions is you want to make sure that your solvent starts below the level of the sample of the ink, because if it's above, what happens is the ink can actually wash off down into the solvent, and that's not good. That's not what we want. So the water starts down at the bottom, and as you'll see over time, the water will kind of creep up the paper because the paper absorbs the water. Then the solvent will go up to a particular part near the top of the paper. Now, depending on your cup, your setup, at some point, the water is not going to go any higher. And in fact, you don't really want the water to go all the way to the top of the paper. You want to take it out before the water has reached, the solvent front has reached the very top of the paper. And then you want to mark with a pen or pencil where that solvent front ended after you take the paper out of the cup. The reason for that is that you'll notice all of your papers are different sizes, and this is on purpose. Now, this might be a lot easier of an experiment if we had all of these on the same exact piece of paper, and we could just look at them side by side and say, oh yeah, this one looks exactly like this one, therefore it's got to be this one. Because they're different sizes, that kind of makes it a little bit more difficult, because in a big piece like this, the solvent might be able to make its way a lot higher than on a shorter piece like this. And so it's going to be hard to compare, as we say, apples to apples between these two. So what we do instead is we calculate something called an RF value, or a retention factor. And you don't actually have to calculate these, but it might be helpful depending on your identification. The RF factor is just how far did the compound travel versus how far did the solvent travel. So what you might do is, after the experiment's done, you're going to measure the distance that whichever particular color you're interested has gone. So let's say we find like a red color that goes up to like 4 centimeters. And then we let the water go all the way up to 6 centimeters. So then the RF value would be 4 divided by 6, or about 2/3. So the reason that we do that is that value should be the same for every piece of paper for the same compound. Because even if it looks like it went farther on the bigger papers, the ratio between how far the compound went and how far the solvent went should still be the same. All right. So it should still be the same ratio, even if the actual distance traveled is farther. And that's why we've got the ruler, and that's why we measure those out. So that way we'll be able to compare between the bigger and the smaller papers. All right, so let's get one of these started, and you can kind of see how it goes. All right, so I'm going to put a little bit of water in my cup. All right, a little bit of water. And then before I actually drop it in, I just want to check and make sure that my water is not too high so that it's going to wash it out. I want to make sure that that water level starts below the spot level. And looks like I'm good. Okay, so here's my water. Now I'm just going to set this in. You'll notice in the instructions it says you may want to use a pencil to support it. I also recommend that, a pencil and some tape. I didn't have one here. I forgot to get one. So if you have a pencil and some tape, the better way to do it is to kind of suspend it from something sitting on the top of the glass, just to stop it from like melting basically and falling over. Not really melting, but like, you know how paper gets when it gets wet. So it helps if it has a little bit of support there. All right, I'm going to put this in. And so you can see right away this did not work. This is a big failure. Because what happened was there wasn't enough mass in my paper, and it just kind of drooped down and fell in the bottom of the glass. And so it is actually spreading out the ink down there, but it's not doing it in a linear, measurable fashion because it just fell down. So not helpful. So definitely use that pencil for support. All right, I'm gonna, just so I can show something, I'm gonna see if I can do better with one of these taller ones. And I'm just gonna hold it with my hand. So just because I don't have anything else. So I'm gonna take another one here, and I'm gonna set it in there. And I'm just gonna kind of hold it there so it doesn't fall down. And I'm gonna let that water go up for all right, looks like I cut out for a second here, but we're back. So if you missed that last comment, it was that we want the solvent, the water, to get close to the top of the paper, but not to go all the way over the very top. I should have grabbed some tape or something because my hand's getting tired now. But it's going. I don't think it's going to take 20 minutes. See if I can show you this here without messing it up too much. So what you see the kind of stripe that's coming up from the bottom. And right now it just kind of looks like a stripe. You're just starting to see the separation of ink. So I'm just starting to be able to see at the very top of it that there's some blue and some purple that are starting to separate themselves out. And that's why we want to let this go as long as possible, because we want those inks to have as much time to separate. Right now, it looks like the different inks don't have that big of a difference between the water and the stationary phase, the paper. So we want to give them plenty of time to try to separate out as much as possible. All right, so while we're waiting for that, let me know if you have any questions. All right, while we're waiting, there's other interesting things you can do too. So this document shows some of these like two-way chromatography, where you're separating things out one direction and then also running it in the other direction. So when things have really close, like so for this example, let's say these two chemicals went up almost the same amount, so close that it's impossible to tell the difference. Well, if you then run it in a second direction, you turn it on its side, now you might be able to separate those out better. Another thing that happens sometimes is there's invisible, where does it say up here? Oh yeah, I think it could. So sometimes the things you're looking for are just invisible chemicals. In fact, most of the time they are. Most chemicals are colorless or just sort of white or whatever. So sometimes when we do chromatography in lab, we don't actually see the chemicals, so we need some other way to detect them. So sometimes that means treating them with some sort of a dye, like in this case, ninhydrin or iodine. Sometimes that means exposing it to UV light, where you might see those differences. And sometimes that means actually using some sort of instrumentation to detect the chemicals or the compounds rather than just paper like this. But an analog to paper chromatography called thin layer chromatography, which is a thin silica layer on a plastic or glass sheet, is often used in the most high-tech professional labs. It basically works the same as this. You're using some slightly different solvents and some of those development methods to detect invisible things, but it's basically the same thing. All right, so we're getting some good separation here. See now? See that big stripe coming up there? And you can definitely see some differences in the colors. So it looks like there's a really light blue that's all the way at the top of the solvent front. There's kind of a purple that's a little ways down, and then almost like a brownish or a yellowish color that's stopped a little ways above the spot. And then there's a decent amount of ink still really stuck at that spot at the very bottom. So again, as I said, I would let this go, let the solvent go as far as you can until it gets near the top. What you might find, especially with these really long pieces, is that it just stalls eventually, and the solvent front stops moving. And that's partially because of evaporation, because the water is evaporating as it goes up. And depending on the shape of your cup and stuff like that, can have some other effects as well. So when it seems like it's stopped and it's as high as you can get it, then you can take it out and let it dry. And remember, mark that solvent front, because as soon as the water dries, you don't know where it stopped anymore. So I'm going to do that here. It's actually still too low, but just because I want to kind of keep this going and talk about the next steps, I'm going to take it out and mark it. All right. So again, it's a good idea to mark with pencils instead of pens, because as we're seeing in this experiment, pens do move around with the water and they dissolve in water. So we generally want to make our marks in pencil. And so you can see I turned out with something like that. So there's clearly this like light blue ink way at the top here. I don't know if it's coming through the camera, but there's a light blue ink there. There's some like kind of blue and a pinkish ink right here. There's some more pink and purple down here. There's something that looks yellowish to me, kind of right around that area. And then there's a darker one here, and then there's still this spot down here. So when we calculate our RF values, we would calculate a different RF value for each ink. And some of this, as you can see, is really estimation. Like I'm going to say, all right, here's this light blue one, and I'm going to give that an RF value of 1 or maybe 0.95 or something, because it's basically all the way up at the solvent front. Then I might try to give an RF value to this yellowish one, because I don't know what it looks like on the screen, but to me it looks pretty obviously like something different that's there. So I want to know about where that is. And maybe the purple one too. There's no specific directions to how many RF values you have to calculate, but remember the goal here is to ultimately identify an unknown. So if we want to know what types of inks are used in the unknown and what types of inks were used in the known one, we can use those RF values to compare and make sure that we're comparing dyes correctly. All right, so I'm going to set that and let that dry. And while that one's drying, I'm going to start this unknown one. So I have a little unknown one. This one I'm definitely going to have to hold because it's so small. And we'll just see if we can get a little bit started on it and talk about how we can compare those. The other thing I would do at this point, if I weren't busy holding this and talking to you, is I would start writing in my lab notebook. So I would talk about that first failed trial, especially because we don't have the supplies to redo this stuff right now. So I totally burned one of my samples, the one that said PM. I'm never going to get a good chromatograph for that now because I screwed it up and now it's done and I don't have another one. So I want to make sure I put that in my lab notebook, because when it comes time to go identify that, I want to be able to know, hey, I screwed this one up. I don't have that one as a reference. So if my unknown comes out and it doesn't seem to match any of the other knowns, then I'm going to guess it's probably that PM one, because that was the only one that I wasn't able to do. So all of those kinds of things, your failures, your successes, whatever, all of that needs to be described in the notebook, so that it can help you later. Once the chromatograms dry completely, you can actually paste them or tape them right in the notebook as well, so that you can see those, and you can you can write on them after they're dry. You can annotate them. You can calculate the RF values and write them directly on and say, like this spot is an RF value of 0.5 or whatever. And then again, yeah, like anything weird that happened, anything that didn't seem to come out quite right, anything that might positively or negatively affect your results and your identification, you should write in your lab notebook, so that you can make those conclusions. You can figure out what's going on. All right, so this one's going, and I can already see just by looking at it, it looks quite different from the one we just did. So even without calculating RF values, as you'll see, I think we can make a pretty good, clear um, conclusion that this unknown is not that standard that I just did. All right. Any questions? Anything else you want to talk about while I'm waiting for this strip? Another thing that can be fun with this, if there's other people in your house that might want to participate, have everybody get a cup and have everybody do it simultaneously, and you kind of watch, and it'll be done fairly quickly, and everybody will have a good time with it. Nothing wrong with that. All right, this one still has a ways to go, but I'm just going to stop it so we can move on. All right, so you can see with this unknown, I did not let it get very high, so my solvent front is right there. Ideally, I'd want it up here because the higher I can let it go, the more separation I'm going to get in those colors. All right, so let's take a look. Here's that first one I did, and then here's this one. Now, it's pretty clear these are not the same. You've got some like yellow and red inks in this one that are not in this one at all, which by itself is pretty interesting, that these were two indistinguishable black marks, black inks, but one is made out of these dyes and one is made out of these dyes, so very different. This one also, you can see that it has some inks that are extremely well bonded to the paper that have stayed way down at the bottom, whereas this one has almost nothing remaining down at the bottom, and all the inks have moved upwards. Now, if we wanted to know, for example, if like this blue ink and this blue ink were the same, or if we wanted to guess that they were the same, I guess we wouldn't really know for sure. But if we wanted to guess that, then we could calculate those RF values and say, well, it went up 0.7 on this one and it went up 0.7 on this one, so maybe they are the same. You can also use your color skills to kind of compare those. If you can't see color, if you can't detect the different colors, and you don't have anybody in your house that can help you with that, it's okay to use other observations as well. So things like watching the black dot at the bottom that doesn't appear in this other one is a good clue that that they're different. And if you see the shapes and the kind of general way that the colors separate, even if you can't actually see the different colors, that should still allow you to make that identification. If you're having a lot of trouble with it, and you need some help, just let me know, and we can work something out there. All right, so I think I've narrowed it down that it is not that first one. And then so that only leaves me a couple more to do since I screwed up one of them. But I'll do the other two, and I'll try to see if I can ID that and then write about it in my notebook. So that's the lab. We go back to the directions here. So remember, there's 3 parts of your lab grade for each lab. There's your pre-lab, so how you set up the notebook beforehand. Then there's the in-lab work. So you get points for just doing the lab. So part of that is the in-lab, that you just did it, you collected data, you've got your chromatograms in there. If you ruin them or for some reason they can't get in your notebook, you can also draw them. So you can draw how they ended up looking in your notebook, be as specific as possible with describing the colors or the shapes or the RF values. But the best, as long as there's no hazardous substances, which there aren't with these, the best thing is to just put these directly in the notebook as evidence that you did the lab. So points for pre-lab, points for doing the lab and taking observations in your notebook. And then the rest of the points are for answering questions, reflecting back on your work in the lab. So you can see that here with the report where you're explaining what you observed, answer the question, are the black inks identical? What was the unknown? And then there's a how science works model that you can use to interpret your data and think about it. And so it asks you to answer some of those questions. So that's what your lab is based on. And remember, the biggest part of your grade in this whole class is your lab work, is your lab notebook work. So please take this seriously, do it, have fun with it, try to get it to work, and take your data. And I'm excited to see how it goes. In addition, this week, lab-wise, you also need to propose your first at-home experiment. So all the stuff is due on Friday, and then I'll be working this weekend to try to go through all of your experiment proposals and make sure to approve them so you can get started on the experiment. When we start into Unit 2 next week, please remember not to start your experiment until I've had a chance to look at your proposal. I just want to make sure everything is appropriate and reasonable for what's expected. So that's lab. I'll stick around for a couple minutes if there's any questions, lab related or anything else. And otherwise, I will see you online, and I'll see you on live on Friday. That's the day everything's due, so I'm expecting there's going to be maybe some questions, maybe not. But that's more what will look like. What Friday will look like. Like what are these specific assignments supposed to look like? Oh, I can also show you. So here's the one that I messed up. Now you can see it did end up kind of making a sort of a streak, but it goes in 2 directions. We just can't use this. There's no data here. We really want a nice chromatogram like that. Ideally a little bit higher in the paper, if possible. Yeah, how to give the strips the score. Good question. So the RF value, it's not per strip, it's per ink. So let's actually just do one now that we've got some of these. All right. So I want to know what's the RF value. Oh, I'm going to try to do this without tearing it. Yeah, okay. So I don't know if you can see this, but there's like a pinkish spot right here. And I want to know what's the RF value of that pinkish spot. So here's how it works. First, I'm going to measure the entire range. So from the very bottom of the spot to the very top of the solvent front, where the water stopped. All right, and then that looks like to me with this ruler, looks like 6.45 centimeters. Right there. Let me go to 5. 5.45 centimeters, right to the center of that spot. All right, so 5.45 centimeters. That's the total. No, I was right the first time. Sorry. So from the bottom of the spot to the solvent front to where the water stopped. No, I wasn't right at all. Hold on. 6.35. So I'm talking about, I'm going to draw it on here so I can show you. I'm talking about this range from the bottom of the spot all the way to where the water stopped when I took it out. All right. So that's my denominator. That's 6.35 centimeters. Now the top, the numerator, is going to be where this particular spot is. Now, whether you use the bottom of the spot or the middle of the spot or the top of the spot doesn't matter as long as you're always consistent because it's a comparative measure. So you're comparing between different pieces of paper. So just always do it the same way, just to be consistent. So I'm gonna go to like the middle, what I think is the middle of the spot of that pink spot, and to me that looks like 5.30. All right, I'm gonna draw this on this also so you can see it. So this is the smaller range, is 5.30 right there. From here to that pink spot that I'm interested in. All right, so the RF value is the ratio between those two numbers, 5.3 divided by 6.35, which is 0.83. So I would say that particular pink ink, whatever that is, that pink ink has an RF value in this system of 0.83. So now if I see a pinkish ink on a different strip that seems to be about in the same spot, I can do that same measurement. And if they both come out to about 0.83, then I can say, okay, well, that's probably the same ink. So if I'm trying to compare a couple that look really similar, then I might say, okay, well, they use that pink dye in both inks. So just to show you, so it's not the strip that gets the score, it's the individual different spots. So let's say then I wanted instead to look at this this yellowish ink that's like right about there. So I would do the same thing. My denominator would still be 6.35 because that's the whole as far as the water went. But now my new value would be down here somewhere. So maybe that's 2 centimeters or something. So I'd have a much lower RF value for that one. And that's what allows us to compare against different size strips where the ink might have gone different absolute distances. My guess is, depending on how it turns out, my guess is that it's going to be pretty obvious. But if it's not, or if it's unclear, that can be a nice way of figuring out which ink is which. Does that answer your question? Does that make sense? All right, great. Okay, anything else? All right, well, have a great week. Stay safe in the snow and the pandemic and all that stuff. And let me know if you have other questions. As you start turning stuff in, I'm gonna start getting it graded. Stuff I've seen looks great so far. So nice work. And yeah, everything is due Friday night for this first module. All right, thanks everybody. Good night.